esteemed academics and ladies and gentlemen. It is with immense pleasure we warmly welcome each and every one of you to the 43rd edition of the Inaugural Lecture Series brought forward by the Faculty of Graduate Studies of University of Madras. Without further ado, let's commence the day's proceedings. To officially commence the day's proceedings by introducing the professor for the day, Professor Uthayasanker Thayasivam, I very respectfully invite Professor Bihan Jayas from the Department of Computer Science and Engineering of Faculty of Engineering.
Thank you. Good afternoon, everybody. And it is my great pleasure to introduce Professor Uthayasanker Thayasivam, who is a distinguished academic and researcher in the field of computer science and engineering. Currently, he is the head of the Department of Computer Science and Engineering here at the University of Madras. And his academic journey began with a bachelor's degree in Electronics and Telecommunication Engineering, also from our university. But after that, he went for his postgraduate studies to the US and got a doctoral degree in semantic computing from the University of Georgia, USA. After that, unlike some of the people who continued in research, Udaya joined the industry and worked at a number of leading companies including Google, Microsoft, Ask.com and Glassdoor in the fields of natural language processing, machine learning and data science. And his focus has always been on scalable and applied solutions. So not just theory or research for research's sake, but on scalable and applied solutions. He has only 150 papers and his X5 index is 15. And in addition to the work at the head, he leads DataSearch, a multidisciplinary research center on data-driven decision making through analytics, engineering and artificial intelligence. He is a two-time recipient of Sri Lanka's E-Swabhimani Award for various products and projects which are used or which can be used to improve the life of people in Sri Lanka. And he also leads the open source research initiative IU, contributing systems, datasets and tools to data science and natural language processing community. Now, as the head of the department, now for almost 3 years, he has led the department in successfully introducing the data science stream both at the undergraduate and master's level. So we have actually moved from being just a Department of Computer Science to a Department of Computer Science and Data Science, or whatever you want to call it, whatever is the current name, machine learning or whatever is the most popular word. But anyway, and he has always led the department to adopt the latest technologies and increase student-centered learning. So Dr. Thayasivam brings a unique blend of academic excellence and practical industry knowledge doing research and teaching. So with that, I would like to invite Dr. Thayasivam to give his inaugural lecture.
Very good afternoon, everyone, and thank you so much, Professor Bihan Jayas, for that very kind note. Looking for set up the Zoom with sharing screen, and then I'll start the lectures. Again, very good afternoon, everyone, and thank you so much, Professor Bihan Jayas, for the very kind words. He has been a teacher to me. He taught me networks when I was an undergraduate, and then he hired me to the department. He mentored me. One other work that we have done a lot is contributing to our local language, and he is the director of the center, and under his leadership I learned a lot, and that helped me a lot to shape into who I am right now. So thank you so much, sir, and truly appreciate your inspirations as well. And I have more to talk about him. I'll come because that's part of today's talk I'm going to present as well. So today I'm going to talk giving language a computational form, from characters to meaning, then meaning to embeddings, and then embedding to voice. That's the journey I'm going to present. So I'll start with a background, introduction to my talk, and then I'll introduce you encoding, followed by that I'll introduce semantic web, then information retrieval, then word embedding, followed by that briefly touch upon low resource NLP and what we do around it in this context, and then finally give a voice to the text. Broadly, like my journey and the talk journey is going to be from characters, meaning, or rather concept, from their embeddings, and then from there to expressions. So a large portion of myself have been introduced, but for the benefit of this talk, I'll just briefly touch upon a bit about me. So I started my education in St. John's College, my secondary schooling. Before that, I was also like my primary school was in Jaffna, and then I was displaced to Colombo, and then I started my education journey at Colombo Hindu College, where I gained a lot. I was head prefect at the school during their golden time, and then gained a lot of leadership. And then I joined Department of Electronics and Telecommunication here at University of Maratua, graduated there. Then I went to USA for my doctorate degree. I've worked in some of the leading industry, as Professor Gehan has mentioned, like Google, where and then Microsoft, Accenture Technology Labs, Ask.com, Glassdoor, everywhere it was mostly connected to NLP and data science, one way or the other. Predominantly that I work in information retrieval, where we need to tell the computer what a text is, what a corpus is, what is a website is, what is a job ad is, right? And then the computer can understand and present. Senior lecturer, head of the department, then NLP Center, I was part of the founding member, and then data search, also the director currently am. And also I'm leading an open source platform where a large amount of data and code that we generated has been shared. With that brief recap of what my journey is, let's get into today's topic, right? Why we need these computers to understand language. Language is how humans store knowledge, share ideas, build civilization. We fight for language. We express ourselves using language, and language define us, and we define language. To give machines language is to give them a window into what we think, what we have thought so far, what our history was, and what the knowledge so far we generate. This is hopefully will help machines to serve human better. Hopefully. So knowledge at scale, right? So by giving computers an access to this large amount of literature that we have developed, the corpuses that we have developed, the books, the recordings, the lectures, the web, the social media, will let computers to understand the knowledge at scale. Inclusion, right? By allowing computers to understand multiple languages, right? It's more than simply understanding knowledge, it's about equity, right? Of the world's 7,000 plus languages, only a handful are well represented right now in computers. So that's very important that we provide computers a multilingual understanding. Then access them, right? By providing not only textual understanding, the visual understanding, that is the characters that are written by us or typed by us or spoken by us, the voice, right? So that gives computers a way for it to converse with us. That enables more people to use computers better. And last but not least, discovery. It allows computers to figure things out on its own. This is where the new era is very much focused on. For several decades we have looked into, but now we feel the doors have opened for computers to figure out, come up with new knowledge. So truly there, let's look into this talk further. So just to give you an idea, if for us a word, like for example, love, it's a word. It has meaning to us. There's an attached to it. There's an intention behind it. There's a relationship to that word. There's a context where we use it matters. So for human, a language is always very different. But for machine, right? It's symbols, it's numbers, it's the token, or the vector that we represent a word of maybe a probability of that word occurs before or after word. So there are two different worlds that we are looking at. And as a natural language processing engineers, our job is always to manage these two. We see whether we can map the human view, the computer view, and make computers do better and brighter and useful decisions. The bridge is representation, right? How we represent the word love to computer matters. Like the better we represent, the better the human computer understands. The better the computer understands, it becomes better for it to make decisions. a brief history of making computers understand language, right? It started way back when Alan Turing started his experiments with symbols, where the computers can understand symbols. The earliest experiment of AI with computers, right? Then came the rule-based approaches where you are writing simplest rule in computers, singular plural rule, other grammar rules, spelling rules, and see whether the computers can use that to enhance language understanding. Then came an era where statistical and linguistic approaches popular. 1917 and 80s were dominated with probabilistic approaches of language understanding. Right? Distribution of words, distribution of phrases started to dominate. That understanding helped computers to understand our language better. Then came the machine learning era, 1990s to 2000, where models learn from data, then they better understand how we write, what we write after one or the other, what is the sentiment behind the text, and that's dominated that. Then deep learning came into the picture. Deep learning revolutionized the way that we understand language slightly, and especially with self-learning, the modern day, we are in 2020s, end of 2020s, large language models popping. So they GPT, cloud, Gemini, hot topic of the modern of today, where understanding context and generate text is the new way we are looking. So from understanding a language, representing language, we are into a phase where we're generating content in language. Let's start with characters. And I mentioned at the beginning of the talk that this talk has some relevance to computers, right? That's the here it comes. So how computers start to understand characters, right? We type in our keyboard, it goes in as a number into a computer understands that number as a specific character and it displays that character. That's how it starts. That's the step one of computers understanding a character. It's known as encoding. Way back, it was ASCII, which was a standard for encoding characters, which is predominantly looking at only English or Latin characters. So other languages didn't have a space. And then came a problem where how we incorporate other languages. There's like 1,500, more than 1,500 languages, more than 600 scripts. The world is diverse with various languages and scripts, but the early day computers were predominantly only English. So this is where the Unicode came. The picture Unicode went through various revisions, and in that exercise, we are representing Sinhala and Tamil. Professor Dayas also led that effort from our end, and many of us know that some of the Hall of Fames in this country, like for cricket, Sangakkara, for some of the things, I think for internet, for his effort, Professor Dayas is now the Hall of Fame. So that's the connection I said, like when he introduced, I will come back to the talk. So it's all started how we represent characters from computers. At early days, computers can understand characters and display. That's so. It doesn't do any other inference. Later, we started at small rule-based engines to do some basic grammar corrections or spelling suggestions, but that was too early, right? It was still at early stage, the computers were still understanding characters. As this situation was growing in, then people were looking at how we can let computers to understand the meaning of it, right? How we can enable computers to infer knowledge. And this is where, I had introduced ontologies. So they look at ontology as a way to define knowledge. This, exercise, semantic web exercise where my doctoral degree is about, started in the late 90s, early 2000, where things were a lot interested about, like people were very interested about, can computers infer new knowledge? To do that, what we thought was, if we can represent knowledge as a graph, computers can traverse through that graph and identify new knowledge. That graph is what is known as ontologies, where concepts are entities and relationships between concepts are being defined. The formats like OWL and RDF were used to define the knowledge. And the whole idea is people will create ontologies of their domain, biology, chemistry, physical chemistry, like each subdomains, and putting all this knowledge together, let the computers traverse through the channel for the same way it can now traverse through the web. So the whole idea was semantic web is the vision at that point of time. A lot of companies try, they keep releasing ontologies, understanding ontologies, try to look at the boundary of inferencing logic in graphs. And that's the era where I get into my doctoral degree. So people started to put out various ontologies, universities, government agencies, chemistry experiments were documented as, in ontologies. DBpedia was converted into Wikipedia was converted into ontology, which is known as DBpedia, especially the names of the people in the Wikipedia. So large amount of exercise to convert an information into a graph was happening, and that created a lot of redundant information. Same concept has been defined two different ways. For example, in one ontology, we'll talk about person, another will talk about it as human. Same concept, right? So this is where I looked at how we align ontologies in an efficient and effective way. That was my predominant, my major effort of my doctoral degree was, right? So with ontologies keep coming into the picture, right? How do we align ontologies? So the next challenge that came into the picture, and we were looking at ontology. Like when ontology, if you look at ontology alignment, that's not straightforward. Why? Because if you want to align two ontologies, in this example, if you look at it, book to novel, novel is same as book, is equal relationship, it's a substantial relationship, so there is more complex way these ontologies need to be aligned for it to be made efficient, right? So that's where I spend a lot of time, where we were looking at both synthetic information, the semantic information of entities, and the structural information as well, to see we can align on those. So some of my work during that time, published in some leading AI conferences and journal, even now, like AAAI and JAR, from the top US, AI-based conferences. My work was predominantly, as I said, scalable and efficient ontology alignment. I compete in one of the international, ontology alignment competition and ranked second in that. And actual rank second means there are different benchmarking. Some of them I led, and some of them I didn't. My approach, and then altogether overall it was ranked second. And on top of that, we were heavily exploiting the famous corpus known as WordNet, which is census, which defines synonyms and senses. We were leveraging that for the benefit of alignment. And the whole exercise at that time was, can we really align ontologies to further infer? So people were looking at inferring knowledge from ontology. So now we have represented information in characters to knowledge graph, and see whether that can help computers infer knowledge further. And at this time, what the people found out was it is inferring logic, right? The algorithms to infer even the simplest thing from the smallest ontology takes a long time, right? Some of them are NP hard and NP complex algorithms. These inferring logics is not going to be bounded. It's not going to be straightforward. So there start the end of the semantic. People stop publishing, RDFs. People realize this is not going to scale, and this path stopped. Didn't really move along. So people tried. People still, at a stage where they were representing, characters. But parallel to this world, there was another way people were trying to represent text or language computers, and that's information. So after my doctoral degree, I went into industry where predominantly I worked in information retrieval computers. Information retrieval, as in you search something, information is required, right? And so we were like representing word as a list of characters. Then we moved into a different way of representing word. And that is what is famously known as Boolean retrieval. The idea is very simple. Each word is represented as a vector of list of documents in your corpus. And you just mark whether that word is present in the document or not. That is why it's called Boolean, right? It is also famously known as one hot, because there is only few ones and a lot of zeros. It's also, one embedded, right? So this Boolean, the binary matrix just says whether word is present in a document or not. That was powerful. And these were the early library search systems that you might have built or you might have used. A lot of search engines started popping with this idea, and they were very powerful. People were able to quickly search through large corpus, list of books, digital content was very useful, and this defined the fundamental information system. Right. This was obviously a little before, this started quite before the semantic web arena, but in my life journey, this came into the picture right after the semantic web, right? And then it was further enriched into something known as TF-IDF because we were not predominantly looking whether a word is present in a corpus or not, or a document or not. We were looking whether how many times that word is there. Right? The word frequency started to define its import. So that started to change the way how we start to understand the word. Now, a word which was list of characters, which were nothing but list of numbers, now changed into a vector. A vector where each dimension is a document, right? It could be a book A, book B, book C. Like each is a document, right? And where in each dimension, what we are going to tell is that how frequently this word is used. That's where it starts. So we started to, represent a word very differently to computers at this point. That gave a lot of search power. Like you can do AND queries, O queries, not queries. So you can actually search in computers things without this word, things with two words, things with a word, OB. This is the power that provided to computers by representing text in this way. And from here, right, during my industry career, right after my doctoral degree, like I work for enterprise search, which is predominantly means that you have a special search engine built for enterprises, a sensitive information circuit, like for example, SharePoint, right? You build your own search box. Then web search, that's high scale, very speed, globally catering audience, with like various languages, and that's the other thing we work with. I work, and in a broadly speaking, there are two kinds of search. Like one is information search we work, that is general purpose information that we go and look for, like what we do in Google. The other one is specific entity search, like job search or X search or product search. They are also very broadly speaking coming under search, but they are slightly different from information search. So these two kind at enterprise to web scale, various scales I have been working, and that is where we started to figure out that representing just words as its occurrences in the document was nothing. It was not giving enough information about word, right? And we were stuck at certain places, like how do we handle synonyms, for example? How do we manage spelling checkers? Like we need more. We need to understand grammar. We need a fundamental meaning for the computer to understand the whole context. This was only limited to returning results, but nothing beyond. And this is where we went further. We gave it to embeddings. So in embeddings, the idea is very simple, right? It all started way back the concept from Phil, that you shall know a word by the company it is. You shall know a man by his friends. This is any other famous quote, right? Same goes to words. You can know a word by the company it is. Word that appears in similar contexts have similar meanings. That's the derivation, right? So we can predict a word from a context or company and vice versa. So what we started to figure out is that we started to build machine learning models where we give a context. For example, in this case, the cat is blank on the right. So we infer the word that is between the first two words and the next two words is set. The cat sat on the mat. The rest of the sentence is not necessarily given as a context. The context here is plus 2 words minus 2 words. So I keep calling this as the filling the blank exercise, right? So basically we started to give a computer a power to fill the blank. You will later realize this power is far more powerful than it may look, right? This is what we give as exercise to us, kids in schools, right? Finals, filling the blanks. But this is what we taught computers, and from here, what we found out was using this, way, we can figure out a vector representation for word. So then each word started to get a vector representation from this learned model, unlike the previous case, which is each dimension is a document. This will give you a dense vector, which will be like 300 size. Whereas in the previous case, now think about the number of documents in the whole word, right? That would be like large number, right? So we'll actually have a really large vector, which is sparse because a word does not appear in all kinds of documents, except for words like is, the, right? So What will happen from the previous, vector representation to here is that this is dense vectors and this is very popularly known as word embeddings, and this defined the later part of it. So there are two ways to derive these dense vectors. There is one is the CBOW, the continuous background approach, the other one is the scriptgram. Leaving the terminology out, the simple idea is that whether you are predicting a word from the context or the context from the word, that's the two different idea here. You can say that, like for example, input is the word set. What are the different contexts that this word could appear? If you can predict that, that is one kind of a model. So using this model, we started to represent words that give words very powerfully interesting outcomes. For example, you can add words because they are two vectors. And when you add words, even the previous case you could add words, but does it give a meaningful outcome? Well, it started to give meaningful outcome now. The simplest, very popular example is that you take a word like he, and you can reduce the word man and add the word woman. They'll come very close to the word in the vector space. And that's where representing words for computers started to get more power. So now the word has meaning, and that is why this arithmetic was possible. Now we have represented the word as a vector, so arithmetic is also possible. Previously, the way that we started to represent a word, list of characters, or graphical ways, conceptual ways, or other ways like document vector, did not have this power. Now, not only that, even other grammatical structures started evolving in this space, like walking, walk, swimming, swam. So, present tense to past tense, they all started aligning to the same structure. So this is when I was working in the information retrieval companies, and this was just popping into the picture. So we was trying to move from our Boolean-based information retrieval structure that is still the one that predominantly, because even the biggest information retrieval companies like Google or Microsoft are still using, we were trying this at the time. However, more than information retrieval, this way of representing words gave a lot of power for other purposes. However, that being said, we are still stuck at one place. The place that we are still stuck at is that now we were able to represent words as list of characters, then we moved into representing them as a vector, very big sparse vector. Then we were able to represent them as a very dense, smaller dimensional vector space with some semantic and lexical meaning, some grammatical meaning to it. However, we still don't have a way of representing a sentence or a phrase. How do we represent a sentence as well? Then only the computer can understand a sentence. So at this point, we can understand a word with limitations, of course. One of the major limitations I'll show in this approach is that take a word like bank. The word bank has two meanings. One is the bank where we do financial, transaction. The bank where a river bank, right? And then bank is a verb actually, right? So having one vector for a word that has multiple meaning was limited. So when we were presenting these words this way to computers naturally had that limitations of understanding text beyond. And that's where we created the new concept called dynamic vector. Instead of creating static vectors, can we create vectors for a word for each instance in a text? And taking that idea, when I joined, Moratua, roughly 10 years back, as a young engineer and joined the Inaugural Center under the leadership of Prof. They sent me to a summer school in India, Hyderabad, and that's where I tried this idea of sense disaggregation from word, and that project was one of the best projects in that summer school. People were at that point, what people were trying is like, can we create this dynamic embedding or like multiple embeddings? Now we have moved from static embedding to multiple embeddings, that is fixed multiple embeddings. So sense to dynamic embedding, that is we create embedding per each instance of the word. So bank will have, for each sentence that appears, it will have its own unique embedding. That's the new way. So those are mostly like a model driven approach. That is, there'll be a neural network that will have to give you, or a pre-trained AI model that will have to give you the embedding for the word. So, keeping that in mind, now we are going back to the other question that we had. Now we are able to represent the word. Word is beyond simple list of characters. Multiple languages can be represented. It has a vector that is dense and it has sense meaning. But now, how do we make a vector for a sentence? How can we represent a sentence as a vector? Because finally, computers understand numbers, vectors, right? Number vector spaces. So we need a way to represent sentences into that number space for computers to understand. So then if we can understand sentence only, then we can classify sentences into like, emails, for example. You can understand an email, it can easily classify the spam or not spam, right? Otherwise, you can go to very standard automatic approaches, right? So we wanted to give it a lot more power, right? So one way that they said was just sum all these word vectors in a sentence, and that will be a good representation. That worked. It has given it has its own power. However, when you do that, composing like just merging a lot of word vectors, even you can add some weight to it. It's very simple and computationally efficient, and beneficial in that sense. But it declares the word. Like I went to Kandy from Colombo, and I went to Colombo from Kandy has pretty much the same energy because it doesn't really look at all. It just sum it up. It's the vector representation of each word together. That doesn't give us any. The next is that neural network approach. That is, we train an AI model to convert, word embeddings into sentence embedding, document embedding. Now, I want you to think very carefully here. Right? Sentences can be any long. So your input is dynamically change. It can be as small as one word, as long as, 15 words, 50 words, we don't know. But we wanted all these sentences be represented with one fixed size space, where only computers works is. Computer cannot work with very dynamically scaled words in spaces. It expects a fixed model. So to do that, then came the very popular architecture called sec-to-sec sequence that defines the modern day, large language models as well to a certain extent. And this is where the early recurrent networks came, like RNN, LSTM, etc. Then came the transformer, that is the core idea behind the modern tools like ChatGPT as well. So again, here what we are still looking at is how do we represent a sentence into an embedded meaning. And please remember one thing. If you try to encode a large text, right, in using any network, you will lose some context because you're anyway projecting into a fixed space. And this is something very important to remember, right? And this defines a lot of concept that is adding to the modern day element. So now we are able to represent sentences and documents. The next thing that we are interested is what is the space for our language? Because most of these problems needs large amount of data that is in good quality, right? So what about our languages, which is traditionally claimed to be low resource because they have limited digital resources, the NLP tools are limited. Compared with high resource languages like English, they have very limited amount of digital representation, text data, annotated corpuses, developed tools that are, consumable are also limited. Subsequently, its funding and other things also very limited, right? So our languages are underrepresented in this world, right? When it was not well represented in the character space, we contributed Unicode and we were able to do something. Now in the NLP world, what we were doing was like you're trying to build some fundamental tools. So that's where we had IU there. We built like various kinds of data sets, various kinds of tools, and they have been released to public to consume for research work and other useful tools building. And we started to contribute that. And not only me, our department, our research centers has put out really useful, corpuses and tools. Like one of the popular one is the translation one, which I was part of, which translate from English to Sinhala, English to Tamil to Sinhala. Trilingual translation is possible, and specifically focused on government letters or circulars. It was the scope of that, and that was very well used and very widely developed. Corpus is being also very widely used. And then on top of that, we started to release like part of speech tags and various other language tools and etc. While we are working on, uh, filling the gap, catching up with what the other languages have been doing, what we realized later is the technology came and swept this whole thing. So I told you like already that we were working a lot with ontology elements, semantic computing, that was swept. Nobody talks about it in a same way as we do. Ontology is still used very briefly. The semantic vocabulary has given up because it's very difficult to proceed further. So that's stopped there. Now, similarly, this annotated work and that various other small corpuses that we're building and tools that we are building has been swept. Why? Because of this self-learning that has come into the picture. The modern day AI is far more powerful and that does not necessarily need annotated corpus. It just simply need a corpus, and that gives a lot of power. At this point, I would like to pivot further. So we have been talking so far about how we represent text. What happens if it is a voice? Because human have in the human language go beyond seeing the text. How we pronounce a word, like how we stress a word, how we express a word, changes the whole show. That expression adds a lot of meaning to it. We can take the most aggressive word and pronounce it in the most softest way and give a very different meaning. And that's the power of expression. And I was so curious about this, and we started working a lot about that as well. Right? So a voice has three things. Who is speaking, what is being spoken, that is content, and how is being spoken. Right? Here, the content is a text. So we have been representing the content part. Now we want to represent the speaker and the emotion together for the computer, so the computer can understand speech. That's very important, right? So in this, work, some of my work has been, widely accepted. So we were able to come up with a unified embedding that actually encapsulates the whole three things that we said earlier in a very effective way. And we have proven that it outperforms some of the leading international benchmarks. And this has been accepted in the top conference as well. So this is one of my student work that what we did was, instead of learning speaker or content or emotion separately, by learning together, we can actually come up with a better representation. So we were going beyond text representation, that word embeddings, to the modern day contextual embeddings, the word and everything. So we were going into a place where can we now go and also represent other things about this. And here, from here, what we told was, okay, if we can represent text in a unified way, can we also sort of explain? Can we actually demark the boundaries of the embedding and say this portion actually represents the speaker, this portion actually represents the emotion, etc. So we wanted to mark the boundaries of our voice representation. So speech usually, as I said, divided into content, speaker, semantics, and paralinguistic, that's emotion. So then under content you have sentences, words, and phonemes, and etc. Speaker is the who is speaking, the age of the person, the accent of the person, various other properties of the person who is speaking. And semantics is basically the intent behind it. Right? It's slightly different concept than content. Then the paralinguistic, that is the emotion that it is attached to. So current model just put out a vector where all the information are here and there. We don't know where it is going into what. But it represents. When you try to do it, apply it for some application, it works. But that we don't understand is that how it represents. What is represented where? That's treated as a block. So what we were able to do was, like, we were able to segregate that into a nice sort of different boxes, but we were not able to give it like how much strength each boxes actually have, is there is an overlap and etc. To take it further, what we analyzed was like, parallelly, currently, how our languages or other similar languages has been represented across the multiple, LLM models. So we took like some of the leading, voice models that has been out there, and we benchmarked it against various languages in the world, and you can clearly see languages like, certain languages like Tamil, Kannada, Telugu, like, Tamil is one of the, one which actually underrepresented across the world, right? Compared like German or, other languages like Portuguese, they are like very well represented, or English, Chinese, right? Interestingly, like if the language has similarity with some other well represented languages, it's also because, for example, Odia is being reasonably well expressed, unlike like Kannada or Tamil, right? So it shows like the relationship between languages also plays a role in their ability to be represented in the existing model. It is not only about the amount of data that we use under training. Also, another important thing to remember is that sometimes largest model, the biggest model, not always wins, right? So what this put out is a clear gap in the current world when it comes to systems. Especially our languages are not very well understood by the AI. There is still a huge gap. But after proving that, what we want to further figure out is, can we sort of understand it better? Right? Can we understand the voice representations better? Right? In that line, one of the things that we found out was, going beyond from there, is that there is a large amount of overlap among the language representation. There is current model, when it represents a language, the same information is repeated again and again. Unnecessary, redundant information is there. And then there are some important information that is being suppressed. So what we try to figure out now is that is a current ongoing work of me and my student, is that can we represent voice better? Number one. Number two, can we demark the lines where speaker information is represented, where content information is represented, where emotion is represented, and can clearly say which part is represented what. That's other important aspect we are looking at. Third important aspect we are looking at is that for our language, the space for our language. Like, is how effectively our language has been represented, can we improve our language quality? Or the way that our languages are represented in the existing model, because we have been, predominantly using the developed language models in the AI world, right? The developed language models are being published by corporates and other part of the world, where our language is not a priority. But for us, that is a priority. Having access for our language, very effectively and efficiently in this AI gives us a lot of power. That's the effort. That's the reason work. All these are like, last 6 months to 1 year work I am presenting that we have been putting into, and they've been accepted in some of the really top conferences as well. So going further, right? So about this, voice representation. Just to give you an idea here, some of the emotions that are represented here, right? And the confidence score of them in baseline approaches, and our understanding of underlying features. So again, marking the boundaries was the scope, and we were trying to mark the boundary better and better, not just to say this is the speaker boundary, this is where the speaker information is encoded. You want to go further and say underneath the speaker, this is where the power factor of the speaker is encoded. This is where the loudness factor of the speaker is encoded. So we wanted to go further and mark them out. The more and more we decipher the embedding, what we found out is there's a lot of clutter, a lot of unwanted redundancy, and sometimes a lot of unwanted input. So that's the deciphering that we try to do. We wanted to give clarity to this embedding. So currently my goal is to how clearly we can represent voice, the one, Number two, a voice for our language. Those are the two frontiers that we are pushing right. So what this journey produced so far, like ontology alignment, I told you that's my doctoral work, and then we moved to embedding work. We have built the local language embedding benchmarks and etc. tools. Then right now we are into sort of voice. We have done some high-level multilingual understanding and position the gap. We are pushing it further, and we are trying to now bring the explainability portion. So from ASCII, that is just list of characters, we started with this journey. Then we moved into Unicode, where other languages also were able to represent it. Then we gave a little bit of a meaning to that word using the TF-IDS or the Boolean representation. Then we moved into word embedding that gave a lot more power, and it is a lot less, a lot smaller and dense vectors rather than a sparse, bigger vectors in TF-IDS. Then we went into contextual embedding, where each word, each time it gets its own vector, and then adding the acoustic features to that. That is how it is pronounced. We are trying to now give, as you can see, the last image there. This is text, this is emotion, this is speaker, how they are blending to each other. Underneath also, what are the key factors is what we are researching. So that's the journey of my research in a nutshell. And we will keep trying to try to bring more and more context to computers and make computers understand it better. So that's the journey of life.
Our heartfelt gratitude to Prof. Thayasivam for that insightful and compelling lecture, and your expertise and insight shared with us actually have broadened our understanding and insights of the domain ontology. So we are truly grateful to you, sir, and it is our utmost duty to pay our utmost gratitude to our resource person today. To facilitate Professor Thayasivam with a token of appreciation, we very respectfully invite Professor Juan Gopura.
Thank you so much.
Thank you very much, Professor Gopura and Professor Thayasivam. And also with that, we have come to the end of the today's proceedings. So before we conclude, we would like to express our sincere gratitude to our sponsors, Cardios Private Limited, our event sponsor, and also the Daily State, our print media sponsor, and Sri Lankan Scientists, our social media sponsor. So our heartfelt thanks goes to our sponsors. With that, it's time to give you to all of you. It is said that every good day must come to an end. So thank you very much for such an engaging audience today. Looking forward to meeting you all in the 44th editions of the lecture series, Inaugural lecture series. Have a nice day all.